Okay, so thanks again. So I'll switch to English, as in the first lesson. So, in fact, this is the title that was that is announced, and but more generally, it will be the title of this talk and a large part of the next talk. Next talk will be very busy with this idea of a topological system without magnetic field, but today I will prepare things for introducing these Chaire numbers and all this for the next week. So it's just a common title. So last week it was a kind of general introduction about fractal systems, where I defined all those notions of fractal dimensionality, but we are very often discussing the geometric fractals. And today I would like to focus on the spectral perspective of fractals and not on the geometric. So which means that the objects that I will discuss today are mostly geometrically non-fractal, but spectrally they will be fractal. So why is that? So this is the today program. So first I will discuss the problem of spontaneous emission from a vacuum which has a discrete scaling symmetry, a fractal spectrum. Then I will present results from an experimental study of such a fractal spectrum, which is the spectrum of the Fibonacci chain of one-dimensional quasicrystal of polaritons. And exactly the same way that I did last week, I will finish with something that is remotely connected to it, but okay, so it's a way just to think about other things. Again, it's a pleasure to acknowledge people I collaborated with on the specific topics that I will discuss today. The people that were extremely involved are Evgeny Gurevich, Ariane Soré, Eli Levy, Gerald Dan and Sasha Teplayev, and the group at Marcoussis, the group around Jacqueline Bloch and Alberto Amo. Okay, so the idea is that very often, sometimes even without saying it, there is a large variety of problems that are very conveniently described using a classification of spectra. So, in fact, there are three classes of spectra. One is the absolutely continuous spectrum. So this is what we call a commonly continuous spectrum. One is the point spectrum, which is commonly called the discrete spectrum. And those are spectra that we are used to work with. We teach those systems usually. But in fact, most of physical systems of of big interest belong to a third class, which is the class of singular continuous spectrum. And usually we don't really touch them when we teach basic quantum mechanics. And so here are examples of physical phenomena which have very much to do with the nature of the spectrum. Anderson localization, quantum classical wave diffusion, random magnetism, just to mention a very few. And there, depending on the kind of spectrum that you have, we could have very, very different results. So now the question is, what about a fractal spectrum? To which category does it belong? So I think that it's not does not require a lot of knowledge to understand that it's in the third category. It's not a continuous spectrum, it's not a discrete spectrum. So the part one, the first part of the talk, will be an interesting problem to warm up, which is the problem of spontaneous emission from a fractal QED cavity spectrum. So the idea, so this is a picture from Julien. You take this system, which exists, right? And you consider it as a cavity. So there are modes. And you put an atom, two-level system, basically into such a cavity. And you're interested in the spontaneous emission of this system with this spectrum. So about spontaneous emission from different QED vacua, we have different possibilities. One possibility, again, that we teach ad nauseum is the system of an atom coupled to a smooth continuum, to a continuous spectrum. And then the probability to remain in the excited state follows this so-called Wigner-Weisskopf exponential decay. So this is very well known. Another possibility is the coupling to a quasi-discrete mode in a cavity, in which case this probability has vacuum Rabi oscillations. This is also well known. There is a third example that is quite seriously studied, which is the case of a structured continuum, for instance, in photonic crystals, and in which case this probability does not have exponential decay, and moreover, the decay is incomplete. It does not go to zero necessarily. It depends on the structure of this spectrum. And now the question is what happens if we have a fractal spectrum. Okay, so what is a fractal spectrum? Again, I will, for those of you who perhaps were not here last week, I remind you basic things about what we consider a fractal system. A fractal system is a self-similar system, which means a system that can be enlarged like this and reproduce itself ad infinity. And this is what is called the discrete scaling symmetry. Now, an example that also I mentioned last week is this quasi-periodic stack of dielectric layers. So we take two types of layers characterized by optical refractive index NA and NB, and you arrange them in the Fibonacci sequence, which is a sequence that you generate by starting with two letters that you call B and A, and the next words are obtained by concatenation of the first two, two previous ones. Okay, so AB is concatenation. This one is concatenation of this. This one is concatenation of this, etc. And like this, you generate this kind of cavity. And if you look at the density of modes for such a cavity, which means what are the modes that could exist here, the density of modes as a function of frequency fulfills, at least qualitatively, this self-similar picture, which means that we believe that this spectrum has a discrete scaling symmetry, and therefore it's fractal to some extent. Okay, so now I would like to have a more formal description of this fractality. And to that purpose, I define a function, which is the counting function. And the counting function is the following. You consider a window in this spectrum, a window of width delta omega. And this window is centered around a given frequency, omega. And you define the counting function, which is the number of modes that exist in this window around this frequency omega. So this is the window. I mean, now if the density of states could be properly defined, this counting function is just the integral of the density of states on the window. But for fractal system, density of state is not a good measure. So just this is bad to write this, but we understand what we mean. And this counting function now, if I just look at the scaling of this window by a given scaling factor B, which is fixed, then I reproduce exactly the same spectrum, which means that up to a constant, A, which is also fixed. So this is what is written here. The counting function in this window is in fact related to the counting function of the initial window times a given factor. If you do it twice, you get this. If you do it p times, then you get something like this. So you have indeed a discrete scaling symmetry. Okay, so now let's test this discrete scaling symmetry. So this is the equation that I wrote just before. And I know, we saw it last week, that the general solution of such a scaling equation with fixed A and B's is made of a power law behavior with delta omega, where this exponent alpha is related to the two parameters A and B that show up here, times, there is something that you should be able to see, I apologize. This parameter, okay, let me just write this, times a function, which is a periodic function of period 1, which is a function of the logarithm of the width of the frequency window, delta omega, divided by log b. Okay, now this exponent usually is between 0 and 1, and for alpha equal to 0, you recover the discrete spectrum, in which case this is a constant. And for alpha equals to 1, you recover the absolutely the continuous spectrum, in which case this function is also a constant. Okay, so this, in fact, is very general. Okay, so the very interesting property of this solution is that it works also if you now convolute the spectrum by a given function. So suppose that you have a profile, and now you don't want to calculate just the counting function, but you want the convoluted counting function, which means that you just convolute your spectrum by some profile function that you choose, okay? And then this convoluted counting function is again a power law with the same exponent times a log periodic function, but now this function depends on the kind of profile that you convolute with. But it's still a function which is periodic with period 1, but a different one. Okay, so this in fact is very well known, this idea, and bears the name in other fields of a wavelet transform of a fractal measure. Okay, so this is a technique that is very well known in turbulence, for instance, and that has been popularized by a variety of people. Okay, so how does it work for our Fibonacci case? So in which case we consider this kind of convolution, and we ask whether this is indeed something that behaves like this. We consider, for a reason that we will see in a second, this convolution, this profile. So this, we test this spectrum with this profile, and if we look at a large time limit, or x goes to 0, then we probe this, and what we obtain numerically is this for this convoluted function, okay? So here you see the two characteristics that were announced. One is this power law decay with an exponent here which is between 0 and 1 indeed. And this exponent, by the way, we can calculate it analytically, completely, and this is the result. So you see that it's not bad. And this modulation by this log periodic function. So indeed, for this is the result that was announced. Okay, so to summarize all what I said so far, a quasi-periodic dielectric stack like this does not have a geometric fractal structure, obviously, but its spectrum has a fractal structure, which is described by this. Now, this exponent is what I called generally last time the spectral fractal dimension, which is, I called it ds last time, but in fact it's not quite this. It's a little bit more complicated due to the fact that it depends on where you define your window. So it could be more complicated, but this is the spectral dimension. Okay, so now I come back to the problem that we defined, the problem of an atom that is placed into this barcode crystal. And this atom has an Hamiltonian, the field has an Hamiltonian, and there is a coupling Hamiltonian between the two, where the strength of the coupling is described by this Vk. So we can solve the time-dependent problem with an initial condition that at time t equal to 0, the atom is in the excited states without photon present. And then the general solution at any time is given by this superposition, where alpha of t is the probability amplitude to stay in the excited state. And the probability to stay in the excited state is the modulus square of the probability amplitude. Okay? So what I would like now to do is perhaps to remind a few basic facts about spontaneous emission for the case of coupling to a continuum spectrum. So I apologize for those of you that did it for many, many years. So but again, as I said last week, you should never underestimate the pleasure you have to hear something that you already know. So the probability amplitude to find the quantum system in the initial state after a time t is just given by this matrix element of the evolution operator. And this is the evolution operator of the total Hamiltonian that I wrote before. And there is a convenient form to write this probability amplitude, which perhaps looks a little bit strange and not so convenient. It can be written as an inverse Laplace transform of a quantity that involves a kernel here, this guy, and this guy is nothing but the Laplace transform of the time correlation function of the field. Okay? So this is an exact expression. And note that this correlation function is local, is a local quantity, which means that in principle I should say something about where the atom is placed in this spectrum, but I won't. So this is for another discussion. Okay? But this is important, in fact. Okay, so there are two relevant energy scales for this problem of spontaneous emission. One is the strength gamma of the coupling between the emitter and the vacuum. And the second one, delta, is the spectral width of this function. Out of those two scales, you can define a dimensionless coupling parameter, which is the ratio of those two. And this defines whether you are in strong or weak coupling. So now if you are in the weak coupling limit, which means that this parameter g is very small compared to 1, then the probability amplitude that we are looking for spontaneous emission is determined by the pole in this inverse Laplace transform, which means the value at which this is 0. And the simplest approximation is to say that this s is equal to minus this function for s equal to 0. And once you work in what is called this pole approximation, you get immediately, this is exact equivalent statement of saying that you have a Wigner-Weisskopf exponential decay. It will be an exponential decay. Now, this in fact is not always true, although we have tendency to believe that it's always true. In fact, at very long time that are much larger than the inverse of gamma, this pole approximation breaks down always, even for free space scalar QED. And in fact, what you have is that this probability amplitude behaves not exponentially, but as a power law. Power law 1 over t to the d plus 1, and this is always true. And this is due to the fact that you have a singularity at the edge omega equal to 0 of the spectrum, and then at some point you must have this behavior. So usually this is not, so it is written in the good books, there are some, but it's not always emphasized when we teach this Wigner-Weisskopf exponential decay. And it is clear that since this comes from a property of the density of states, that this d that is here is what will be eventually the spectral dimension for a fractal, this power law. Now, this power law also holds for structured photonic crystals, but usually we don't really discuss this because this is not achievable, because you will see this power law decay at values for which the amplitude is already 0 by far. So there is no chance to say this, but here will be an example. Okay? Okay, so now for a fractal vacuum, we are always in the strong coupling limit, and even, in fact, if the strength of the coupling here is very small. This is just because the density of states is very singular, that we are always in this strong coupling limit. But the fact that we are in the strong coupling limit does not mean that short time limit cannot be used, what is called the Fermi golden rule. So we can use it. So this is what I'm going to do now. And I will just revisit the Fermi golden rule. So again, this is things that we know very well. Fermi golden rule, we learned it first week of quantum mechanics, second week. But let me just remind you a few basic things about this. So a standard perturbative treatment is to say that for short times, in fact, alpha of t, this probability to stay in the excited states, is close to 1. And therefore, the excited state probability goes like 1 minus something, which can be written like this, where this gamma e of t is just a Fourier transform of the function that we saw before. And this function can be written under this form, which is a convolution of the density of states by a probe function, which here is a sinc function. Okay? So up to this matrix element that we just put in the density of states. So now, so this is the probe that we have, and we look at the large time limit of this function that goes to some value. So this is what we have, and in the limit of very long times and for a continuous spectrum, this turns out to be a delta function. Therefore, this becomes time independent, and we get this well-known result. And this gamma e that we obtain here coincides with the exponential decay rate that we would obtain in the Wigner-Weisskopf calculation. So we are happy. So this is what we do usually. So now, for a fractal spectrum, it's a little bit more complicated because we have to convolute this spectrum, which is this strange spectrum. And therefore, this does not work anymore. Okay? And instead, what you have is just a convolution with this function of this density of states, which has this form. And then what you get is immediately, because of what I said before, that this function gamma e of t will be just a time, algebraic decay with time, with an exponent that depends on the spectrum that we have here, times a given function of log of the time, which is a log periodic function. And this alpha is just the exponent that we had before, and all those constants depend on the considered problem. Okay, how does it work? It works that way. So here, this is the integrated density of states that I showed before. Now you simply convolute this and calculate this quantity, and you obtain, indeed, that it works with this power law decay with an exponent that is related to this exponent of the counting function, modulated by log periodic oscillations. Okay, so this is much more complicated than what we had before for the Fermi golden rule. To summarize all what I said, spontaneous emission from a fractal vacuum always corresponds to very strong coupling regime, and therefore it is never described by a Wigner-Weisskopf exponential decay. The decay probability, in fact, is always given by an algebraic decay modulated by the log periodic function, which is characteristic of the discrete scaling symmetry. So which means that in that case of a fractal vacuum, we are always in this regime of power law decay, in fact. Okay? And this exponent gamma is related to the spectral dimension of the spectrum. Okay, now we can go, so I will go very far here. We can go beyond the short time regime and strong coupling. And if we do this, so what I will just present is a toy model which incorporates the two basic ingredients. First ingredient is to have a singular behavior around a given frequency. So this is taken into account by this. Second ingredient is to put the simplest log periodic function that I could, which is just one harmonic of this log periodic function. Okay? So in this model is nice because it reproduces all what we said in the short time limit. It mimics the fractal properties because it has the right behavior. It has a singularity in the spectrum, therefore we expect this power law decrease, and we can calculate everything analytically for all time scales. And this is what we obtain. What is very interesting is that, this is the probability amplitude to remain in the excited state as a function of time, and this is the probability amplitude, which is the square root of the probability amplitude. And what you see is that if this parameter A is equal to 0, we just have a singular potential, which is a kind of photonic crystal, okay? And if A is different from 0, we have a fractal plus D. On top of this, we have a fractal. And what you see is that it has a very, very important impact on this. The blue curve is for A equal to 0. So you get this exponential decrease of the probability, the spontaneous emission. But you see that at the moment that you put A different from 0, which means that you are in the fractal regime, the probability to stay in the excited state is very high, does not decrease. Here there are more than 3 orders of magnitude between the two. So just this fractal spectrum, this log periodic oscillation is enough to inhibit almost completely the spontaneous emission. And another way to look at this is to say why this happens. And this is another way. If you look now at the probability amplitude, you see that it looks like they are kind of beats, competition between two frequencies. And this is precisely what happens for the fractal spectrum, that you have, in fact, so you have a frequency that is fixed by the two-level atom. Now, because the spectrum is fractal, you don't have usually a frequency of the spectrum that is exactly at the one of the atom, but it's very close. And then it could emit a photon because you see a frequency of the vacuum, but there is another one that is extremely close as you wish, but not equal to it. And in fact, the ping pong is this local interference between two, always at least two, there could be more, frequencies that are close because of the fractal spectrum. So this is why you have this kind of beats here. So it's of course not very clear, but if you think about it, it works. Okay? So it's a kind of interference effect. Anyway, so this is the short time regime. You see, this is short time regime. But if you go in the very long time regime, you see again this decay, and you see those log periodic oscillations here. You see that for A equal to 0, there are no log periodic oscillations, of course, but for A different from 0, you see this log periodic oscillation that show up. Okay, so this was the spontaneous emission. And now for those of you who had a small nap, they have a chance to wake up, because I'm going to speak about something unrelated, rather different, almost different. Okay, so it's you will have another chance for the third part. Okay, so but this is a good one. So now what I will present is an experimental study of such a fractal energy spectrum for the case of cavity polaritons in a Fibonacci quasi-periodic potential. So first of all, I should say very clearly that the Fibonacci problem has an extremely long and rich theoretical and experimental history, and it would be very, very difficult to list all the people that have been involved in this. So here I just list a few. Always you have to choose, so I think that they are among the very, very relevant people who studied this problem. They are experimentalists, they are mathematicians, like Damanik, Barry Simon. They are mathematical physicists, like Jean Bélissard. They are physicists, like Komoto and Jean-Marc Luc. So everybody just did something in this problem, and there are many, many others. So there is still much to be done. And what we did here, what the team of Jacqueline Bloch, with some of the relevant people here, did was to consider now not this kind of stack of dielectric layers, but instead to consider such a potential which defines the letters A and B, and like this, we built a potential according to the Fibonacci sequence, and this is the way it looks like. Okay, so this is one sample, another sample, and this is the potential that we see. Okay, so those samples were made out of 233 letters. So for those of you who asked this question, when do we start to see fractal features? So this, you don't have to be infinite. A finite system is also not that bad. Okay, so this is the Fibonacci sequence. And now, before going further, I should say a few words about cavity polaritons. So the idea of cavity polaritons is, what are they? They are, in fact, quasi-particles that arise from the strong coupling, it's very important to have strong coupling, between an optical cavity mode, just a mode of a cavity, with confined excitons from a quantum wells. So this is this hybridization between the two modes. And this is the system where they live. So in fact, you have a quantum wells that are here at the border between two Bragg reflectors. Okay? And your excitations, they live in this two-dimensional slice of the system. This idea of cavity polaritons, I think, was first, or among the first, proposed by Claude Weisbusch back to 1992. And it proves to be an extremely powerful and useful instrument to probe quantum systems for reasons that I will explain in a second. So basically, for theoreticians like me, cavity polaritons are, in fact, excitations that can be described using a two-dimensional Schrödinger equation, which is this Schrödinger equation. The effective mass of those massive photons is given by this combination, where n is the effective refractive index, EC is the energy of the fundamental mode of the cavity, it is defined here, and C is velocity of light. Okay? So this is this two-dimensional Schrödinger equation. And in fact, we could study the eigenmodes of this equation just by solving numerically this problem. So this is very easily done. Okay? But for obvious reasons, we prefer to define instead a well-controlled one-dimensional problem. And this one-dimensional problem is described by this effective Schrödinger equation with a potential here, V of x, that we have to calculate. Okay, so this is the most difficult task, I mean, among the most difficult tasks. And here is the way that this potential is defined. So let me just define some notations. This W of x function is this potential, okay, that is here. This is the W of x. And x is that direction. It is between 0 and L. L is the length of the system. And for each x, there is a y, a transverse direction, that is between minus half and plus half of W of x. Okay? Now, this V of x is given by the sum of two terms. The first term, for people that are used to do this kind of problem, is a trivial term. It's just a diabatic approximation of changing very smoothly this potential. The second term is non-perturbative, is a kind of WKB calculation. And this non-perturbative correction is rather unusual in polariton physics. In cold atom systems, it is not. There are beautiful papers on this, so for people that are coming from this, they will say, okay, this is very usual for us. But for other communities, this potential is very unusual. And in fact, it describes the steps sharpness of this potential. What you see is that if you have a very smooth potential here, so if it is constant, this potential, then this term is 0. If it is extremely smooth, this could be a very small correction. But if it is very sharp, this is singular. And even it could be delta function potential, a repulsive delta function. So it's a very important part of the potential. Now, I said before that there are very specific advantages of polariton physics. And those advantages are, I think, the following, is that it allows for direct time and energy resolved measurement of the excitations, both in real space and in momentum space. So here, for instance, is an image of the polariton wave function. So this is the x direction. So this is along those chains. So you see the wave functions. But you can also get them from the energy point of view. So you can have both energy and x description. So this is very nice because it allows also to study the wave packet dynamics. I will discuss this at the end in my conclusion. So now what we can measure, what is measured, is typically this spectral function, which is energy as a function of k. So how can you do this? You can do this because, again, in this polariton system, you have a very interesting mapping that, in fact, there are excitations here, there are k's, and if you study by fluorescence, so you excite this gas, they emit, they fluoresce, and the energy that is emitted in a given direction with a given angle here, there is a one-to-one correspondence between this angle and the k wave vector in plane of the polariton, which means that just by scanning through theta, you can get the k. And there, like this, you can get E energy as a function of k. Okay, so this is something extremely interesting. And this is qualitative, this is nice, but what we would like is a quantitative description. So to get a quantitative description, I describe again our 1D effective model, where this potential v of x is the one that I wrote before. I can write it also under that form, where, so this is to describe this potential around this x direction, where now this function is defined by this. It's called the characteristic function. This function is extremely important from the topological point of view, and you will hear about it ad nauseum next week. So just be acquainted with this function. And the second part, which is this potential, describes, in fact, the shape of each letter. Okay? And this is typically what we obtain. This is numerics with this one-dimensional model, and this is the experiment that is measured with this E of k fluorescence. So you see that it's not bad at all. It's quantitative, it's not qualitative, but I would like to insist on the fact that this very nice agreement is due to this non-perturbative correction that is here. If you don't include this part, what you have instead is the following. So here, what I present is on the left panel, this is E of k for either the full numerical 2D problem without effective 1D potential, or with the 1D potential, but with the non-perturbative term, which is this one. And it's the same. It's exactly the same. There is absolutely no difference. On the right panel, what I draw is the 1D calculation, but without this non-perturbative term, which is only this guy. So you see that it looks, so if you like just pictures, it looks very similar. But very quickly, you see that it starts to be extremely different. For instance, here there are gaps that do not show up here. Okay? So this, if you want a quantitative description, this correction is essential. Okay? Whereas a lot of people just were satisfied with this, but it was not enough for us. So this is what we obtained by doing both. Now, as you see here, what we did is that we described each gap by, in fact, an ensemble of two integer numbers. Okay? So here they are. Okay? And how this is called labeling the gaps, to give a name to the gaps. So how is it possible to do this? So in order to do this, they did another experiment, which is different from the first one. And in the second experiment, instead of looking at the energy for a given direction, which tells us about the k that is related to this, we now integrate over all the directions. So, and we get the total intensity of the signal. And what is plotted here, this is the experiment, what is plotted here is this total intensity as a function of energy. Okay? So this, in fact, is proportional to some extent to the density of states. Okay? And so this is the experiment. This is the theory. But you see, this is a different experiment than this one. This is for each given k. This is for integration over all the k's. Now, if you integrate this density of state, you obtain the counting function, which is the function that is of interest to us. And by integrating this experimentally, you obtain this. By integrating the theoretical density of states, you obtain this theoretical counting function. And now here you see that those labels, those gaps that are here. So you may say, what is the relation between the two curves? The relation is that, in fact, it looks like, if you look at it, that this function, E of k, is in fact this envelope here. So if I just turn this and put it here, so which is what I did here, you see that, in fact, you have gaps exactly where there are gaps, etc. So this function, in fact, this envelope is this envelope. Okay? But again, this is not obvious. There are very difficult questions here that took us, made us very busy for a very long time, especially where is the zero here. Okay, so, but if you are convinced about this, then everybody is happy. And like this, in fact, there is a relation between those gaps here and the gaps that we have here. Yeah. Okay, so now how to do this gap labeling. So I remind you this potential that we have. Okay, and now I'll take the Fourier transform of this potential. By taking the Fourier transform, I get a function like this, where this is the Fourier transform of the single letter potential shape, and this is just a sum of delta functions. Okay? And now each pair PQ of integers defines a unique Bragg peak, because this sigma is irrational. Okay? Now, the problem is that Bragg peaks are dense, because this spectrum is a fractal spectrum. It's in fact something like a Cantor set. And therefore, we cannot just use this. We must use what is called periodic approximants. What is periodic approximants? Is to replace this irrational number by a rational number, which is just a ratio of the two Fibonacci numbers that are close to it. And now, by doing this, we built a periodic crystal of length. So A is the length of a given letter, but of length, this Fibonacci number. Okay? And potential, which is this one. So again, now I built a system of length A, of length this, and out of this I built a crystal, infinite crystal, another ad infinitum. This problem is a perfectly well-defined periodic problem for which I have Bragg peaks and everything, and those are the Bragg peaks, which are at values which are given by 1 over A, just these two numbers. Okay? And in the limit where the chain length goes to infinity, this goes just to 1 over A, P plus Q sigma. You're with me? So again, I did something very artificial, which is to build out of this periodic approximant a crystal, okay, of a cell which is length this guy. Okay? And okay, now once you have this, it's very simple. Usually we do perturbation theory. So what I'm going to say now is in textbook material. It's very simple. We say that this is a very small potential. which experimentally is not the case. And then what we know is that for this crystal, which is not a quasicrystal, a series of gaps open at each value of the independent Bragg peaks. So this is just a Bloch theorem, but in perturbation theory, that each time we'll have a gap for each of those Bragg peaks. Okay? And to first order in perturbation theory, each Bragg peak hybridizes degenerate Bloch waves plus minus this Q over 2, and a gap opens at an energy which is equal to this energy. So this is the usual argument that is in the book. Okay? And the counting function, which is the normalized integrated density of states, inside the gap just counts all the excitations that are below this value, and this is just given by this value. Again, this is textbook. Now, this is a derivation that looks nice because we get a result that we like, but this derivation is wrong. Okay, so it just it helps to understand, but it's not correct. Okay, because it's a quasi-periodic system, it's a quasi-crystal. Okay, but what is nice? So this is this value of the integrated density of states of the counting function. So each gap is in fact labeled by two integers, p and q, and each value of the gap here, it's between 0 and 1, can be written under the form p plus q sigma. And then you see that, in fact, numerically and experimentally, it works extremely well. Okay. Now, this result, in fact, the flux? Yes. No, sigma just here is just this quasi-periodic potential. Is sigma. This sigma? Yeah, so you approximate it by the ratio. Yes, this is in order to build my argument. But, so this I said, this is nice because it connects to usual solid-state physics that we are doing usually. But now, this is my statement, is that in fact, this result has a much broader range of validity, and this bears the name of the gap labeling theorem, which was, so I should say that last week I listed the number of 3 mathematical heroes of this analysis on fractals, and we have the chance to have one of them here with us, Michel Lapidus. So then I feel a little bit ashamed to discuss gap labeling theorem that I guess you know very well. So, but this result is in fact valid for very strong potentials and much beyond this loose argument that I just gave now. Okay, and so this was done in 1982. Proposed by Bélissard, and I think that real proofs of gap labeling theorem are still going on those days or the last years. So the point is that what is nice and what is in this gap labeling theorem of Bélissard is that those two integers, in fact, they are not just integers, they are topological invariants. And they bear the name of Chaire numbers, so they are real Chaire numbers, and they are independent of the potential strengths, of inhomogeneities that could arise in your chain, of disorder, of many, many things. Okay? They are just very, very stable numbers that describe, in fact, the bands of this quasi-periodic potential. Okay, so, and again, in order to get that this fits very well between the numerics and the experiment, I remind you that we have to add this part. Without this part, there are just gaps that disappeared, that did not exist, although they exist according to the gap labeling theorem. Okay? So those Chaire numbers here, we will discuss them ad nauseum next week. Okay? But just here they come from this gap labeling theorem. And in fact, the motivation of Bélissard to introduce and obtain them was to understand the connection of this kind of problem and the Hall effect, the integer Hall effect, quantum Hall effect. Okay? So there is a very strong connection between the two, but this we'll discuss next week. So now the other things, what I said at the beginning and I said very many times last week, is that if we want to prove that this spectrum or this integrated density of states is a fractal spectrum, then we know that it has to have this, this decay behavior times a log periodic function. And what we plotted here is, so in red is the theory, and in blue is the experiment. And you see that, in fact, on top of a power law here, which is this, we have indeed a log periodic behavior of the integrated density of states. So this is the indisputable fingerprint of the underlying fractal structure of the spectrum, this log periodic. So again, the fact that it is a periodic function of the logarithm of delta omega makes it quite difficult to observe. But here we have 1, 2, 2.5 oscillations, and I think it's the first time that those log periodic oscillations have been observed in an experiment. So this is really the proof that the spectrum is fractal. Okay. Now, I told you also that we can resolve spectrally and spatially the images of the modes. So those are now the modes in real space. And again, I mean, this is in real space along the chain, and this is in energy. And you see that if you compare the experiment and the theory, it agrees also very, very well. So I finished this part 2, and let me summarize what I said. Okay. I said that the coupling of a quantum emitter to a fractal quasi-continuum leads to an unusual decay dynamics. The decay exhibits scaling properties related to the discrete scaling symmetry of the quasi-continuum. I described this experimental study of a macroscopically coherent polariton system in a Fibonacci cavity, and we showed that it fulfills this gap labeling theorem and spectral functions very well. Further direction is to study the long-time dynamics of a wave packet with a quasi-continuum fractal spectrum to get those log periodic oscillations. So typically, numerically, this is what we obtain. So this is the work of Ariane Sauret. So the quantity that we calculate here is what is called the return probability. So if we build a given wave packet, we look at how this wave packet evolves with time and project it on the initial wave packet and average over time, over a certain window of time. And this function of time looks like this on the Fibonacci. And you see that indeed there are those log periodic oscillations on top of algebraic decay. And we would like very much to observe this experimentally. The only problem that we have is that if you look at the time scales here, we need to keep coherent this polariton gas over a quite large window of time, which is kind of a challenge for the moment, but we are not desperate so far. Another direction is to study the spontaneous emission using a tunnel junction in a microwave fractal resonator. So this is the world champion Fibonacci of Julien Gabelli, which is a Fibonacci of 2,500 letters, which is quite, it's 1 order of magnitude more than what we did before. And it has this shape of a snake in order to put it in a fridge. But this is, and now to put just a tunnel junction inside the system to study spontaneous emission. And let us conclude for 5 minutes or so with something a bit weird that is remotely connected to what I said so far. So the idea is to build a simulator for quantum Einstein gravity. So what happened to him? You know, what's the relation with this poor Fibonacci and the quantum Einstein gravity? So let me just remind you a few basic things about the quantum gravity. So as we know, the Einstein relativity, general relativity, which is based on the Einstein-Hilbert action, is a very successful effective field theory on length scales which are much larger than the Planck length. So the Planck length is this. It's a very small length. And it is built out of h bar and c and the Newton constant, which is extremely small. And the question is, whether it is possible to promote this effective field theory to fundamental microscopic quantum theory of the gravitational interaction and space-time structure. And then further questions are, what are the relevant degrees of freedom at the Planck length? And which aspects of space-time are dynamical at the Planck length? Is it the geometry of the space-time manifold? Is it the topology? Is it the dimensionality? So all are questions that people ask themselves. And the basic tool that people use in order to investigate this problem is this sum over histories, also known as gravitational path integral, which has this form, generic form. And now each path here is a four-dimensional curved space-time geometry, G, so this is a metric, okay? And which could be, you could think of it as a three-dimensional spatial geometry that develops in time, okay? And you have to sum over all possible metrics, okay? But you don't know what they are, so you have to do it dynamically. And the weight associated with each metric is in fact given by the corresponding Einstein-Hilbert action, which is the well-known classical action, okay? Where Gn is the Newton constant and lambda is the cosmological constant, and the values are given here, okay? So this is in fact a kind of Gutzwiller approximation or semi-classical approximation of quantum gravity, if you want, around this classical Einstein-Hilbert action when you look at fluctuations around this. The problem is the following, is to give a meaning to a functional integral over all metrics on a space-time. To give a meaning, it means what is the definition of it, what is the meaning of renormalization, etc. of it. So this is nice to write it, but just it does not bear a lot of content. Okay? And the first thing that we notice immediately if you try to go further with this is that if you want to do perturbation theory, this will never work because of the unusual scaling with mass of the Newton constant. So this is very known, but this is also very unfortunate because all perturbation theory that you can do does not really work here. So it's a hard problem, and there are several approaches on the market. First approach is to leave the framework of quantum field theory and to go to string theory, spin forms, etc. I will not elaborate more because I cannot. A second approach is to stay within non-perturbative, because of what I said, quantum field theory, and to assume that this asymptotic safety promoted by Steven Weinberg works. And this just means that for this d equals to 4 gravity, there would be a non-Gaussian ultraviolet fixed point that you can do physics around it. So this is a route that has been taken by those gentlemen, Martin Reuter and Frank Sauersig in Germany, and I will analyze it. And there is a third option, which is statistical field theory or dynamical triangulation of the space-time manifold. And this is a route that has been taken by Ambjörn Jurkewitz and Renate Lohn. I will also discuss this now. So again, I will not discuss more how they do, but this is what they obtained. So the last option, this statistical field theory, just gives you a dynamically generated four-dimensional space-time, and they calculated, in fact, a spectral dimension. So the title is perhaps a little bit pompous, I don't know. But okay, the spectral dimension of the universe is scale dependent, so it's nice to know, but okay. What they mean by this is that, in fact, what they calculated basically is the heat kernel that we defined last week in details, okay? And this heat kernel is nothing but the integral over the volume of the return probability. And if you remember, this guy was just volume of the manifold divided by this time behavior with a power here, and this, we claim that this was a spectral dimension. So they measure, in fact, this d. They measure exactly this numerically, and they have access to this d. Okay? And what they conclude here is that, in fact, if you look at your four-dimensional manifold at very large scales, it is a usual 4-dimensional manifold. But if you look at it at very, very small scales, Planck lengths, it is different. And this is the result. So what they measured here, so this is their plot, is this spectral dimension as a function of, so sigma is time, is exactly time. So this is the time that is here. And what they obtain is that for very large time, this spectral dimension is close to 4, and this is what they represent by saying at very large times or lengths, the manifold is just classical, it's 4-dimensional. But if now you look at this spectral dimension at very, very small times, which is what we have here, then in fact, this spectral dimension, so here is the result. So this is for very large times, so it's close to 4. But at very, very small times, at Planck lengths, it is close to 2. So which means that spectrally, geometrically, the space-time is 4-dimensional, but spectrally, it is 2-dimensional. So this is their claim. Okay, this is their claim. Good. This is numerics, pure numerics. Now, the second group that did non-perturbative renormalization group flow analysis, which is a completely different approach, in fact, obtained, so this is their result. In fact, so they obtained, wow. They obtained so what they did is a renormalization group using scaling of the two constants that we have in the problem, which are the Newton constant and the cosmological constant. You scale them with the length accordingly. And in fact, you have this renormalization group flow. So they found this fixed point here, which is extremely interesting, that we will discuss in the fourth lecture a little bit more. And close to this fixed point, what they found is that if they calculate the same heat kernel, they find that ds is also equal to 2. So two different approaches, completely different approaches, converge to the same idea that the spectral dimension of a 4-dimensional space-time manifold at Planck length is 2, or close to 2. Okay, so now our idea is to take what we did before. So here, you remembered what we said. We had a system that is not geometrically a fractal, but its spectrum is fractal. And now, just to do it for the space-time, in which case the manifold is not a fractal, but its spectrum should be fractal with a fractal dimension that is close to 2. So now the question, is it possible to mimic, at least spectrally, Planck length space-time that those people obtained using a fractal system with the same spectral dimension? So this is the idea, that now I built a fractal which has a spectral dimension close or equal to 2. And this, in fact, is not very simple because it's very difficult to find a fractal with ds equals to 2. But in fact, we found one, which is this barycentric fractal. Yes. No, the 3-dimensional, well, yeah, okay. The 3-dimensional carpet has also 2.06, yes. And so, but this is our, it is 2-dimensional for a simple reason, is that now this fractal, this waveguide, has a ds that is close to 2. And now if you put a scalar quantum field on it, for instance, polaritons on such a system, or something else, then in fact you could have a simulator of quantum Einstein gravity. So which means that on such a system, you could measure or calculate other physical quantities more than just this return probability or this heat kernel that they are the only quantity that they can calculate or measure. So this could be a simulator of quantum Einstein gravity. And we are very happy about this. And it looks weird, but in fact it happens that we were not the first to have this idea. Many years ago, a respectable physicist that received the physics Nobel Prize for Higgs bosons, François Englert, had a very similar idea, but a long time ago. So this is just taken from his paper. This is the title of his paper, and this was exactly the same idea, which was to mimic, in fact, the metric space-time as fixed point of a given fractal structure. And the one that he found is this one. I must confess that I prefer this one. But as you see, it's not that far So you see, it was not such a weird idea. So this is the idea. So this was the end of this wandering, and thank you for your attention. And sorry for being a little bit late.